Hello everyone, and welcome to class number 39 of Physics 218. So last time we talked about the time-independent Schrödinger equation and the hydrogen atom. We looked at the energy eigenvalues and eigenfunctions. We also talked about angular momentum in hydrogen. Today there's one more thing about hydrogen I want to talk about, and it's a really rich topic, namely spin, and in particular the spin of the electron. We'll say a little bit about what spin is and how we know there's experimental evidence for it. Then I'll talk about something that wasn't in your reading, some really quantum wackiness with multiple Stern-Gerlach experiments. So this is sort of where, this is going to be the bridge between 218 and 421, basically where we leave off, 421 picks up at the beginning. And then I want to end with some applications of spin, because there are a lot of them. I sort of decided that there's enough with spin to spend all of today's class on it. In lieu of a normal recitation tomorrow, what we'll do is I'll give a little bit of a class session starting nuclear for Thursday's recitation. And then on Friday we'll have more time to talk about nuclear processes, some things that we should all know about, and some applications. And then I think Monday we'll be able to reserve for what I would like to do as a synchronous session, just so that everyone has a chance to interact with me and hopefully each other as we review for the final exam. To introduce spin, one of the things that I want to do is to think about historically what happened, and in particular to point out that there are still some puzzles about the spectrum of hydrogen that the Schrödinger equation by itself doesn't manage to resolve. Namely, right, so you learned when we talked about the Bohr atom, right, that when you have a transition from the n equals 3 level to the n equals 2, right? And just remember that this applies whether you're talking about the Bohr atom or the Schrödinger atom, because the Schrödinger energy eigenvalues are exactly the same as what the Bohr model predicts. Right? That this transition is associated with emission of light of a wavelength of just about 656 nanometers. Now astronomers call this the H-alpha spectral line. However, if you go and look at a high-resolution spectrum, it turns out this is not a single line. Rather, it's a pair of lines. And I'm going to go and cut to my computer in a second to show you a picture of this. But one puzzle that remained is, how do we explain that you get a pair of lines, sort of what people call a doublet, in this one transition here. So I'd like to start off today by reviewing some things about magnetic dipoles that hopefully you learned in Physics 118. So classically, right, let's imagine a situation where we have a little loop of current. And I'm going to sort of attempt to draw this in sort of 3D. So I'm going to draw a little ring here, and I'll label a current. We'll imagine we have like a ring in a plane where there's a current circulating in this sort of counterclockwise sense. Well, hopefully you remember from 118 that a current loop is a magnetic dipole, and that in this case, so if you can find the direction of the magnetic dipole moment using a right-hand rule. If I curl my fingers in the direction of the current loop, my thumb points up. And so we say that classically, a current loop is a magnetic dipole. And now I can't remember what symbol you used in 118 for magnetic dipole moment. You see either little m or the Greek mu for it. We already have too many m's to deal with, so I'm going to use mu. So I'll just label that, and it's a vector. So let me draw the magnetic dipole moment vector associated with this current loop. Point up, like so. Okay, so classically, a little loop of current ought to have a magnetic dipole moment. How is this relevant to atoms? Well, let's sort of retrace our steps and start by thinking about the Bohr model of hydrogen again. So let's think about Bohr. Right. So Bohr, right, in the Bohr model, we have an electron that's orbiting a proton. So let me try to draw that. So I have my proton here, and I'll use a different color for my electron. And I'm trying to draw sort of an orbit in 3D, which is why I sort of try to draw it in profile. It's not actually an oval. But if this electron is going around in an orbit, right, then it essentially forms a current. So orbiting electron So remember, there's a connection here in the Bohr model. There's the electron always has some orbital angular momentum, right? Remember that L equals n h bar, right? And so in this case, right, once you have you have some orbital angular momentum here, you have an electron that's orbiting and making a current. So the electron has a magnetic dipole moment mu associated with its orbital angular momentum. Okay. Let's turn now to sort of thinking about Schrödinger and sort of seeing how that suggests how there could be a magnetic dipole moment for an atom. So I'm not going to try to draw a Schrödinger hydrogen atom because I can't really draw those fuzzy clouds of probability density. But what we learned, right, was that right. So I'll just write down the NLM. We learned that those are the energy eigenfunctions, right? So for energy eigenfunctions, right, with L not being 0, well, what we learned last time was that any state that has L non-zero has some orbital angular momentum, right? Namely, the eigenvalue L squared is going to be L plus 1 h bar squared. And then, therefore, so if I think about the square root of this eigenvalue, right, L is non-zero as long as little l isn't 0. And so what we can conclude from this is that the electron should have some magnetic dipole moment right? Following this kind of logic, so electron has a magnetic dipole moment if that quantum number L isn't 0, because then it does have some orbital angular momentum, and you can think of that sort of orbital angular momentum as being associated with a magnetic dipole moment. So this leads us then to the experiment that Stern and Gerlach did. Let me erase the board, and then I'll tell you about that. To understand the Stern-Gerlach experiment, we need to remember something about the magnetic force on a magnetic dipole. It turns out that, sort of like electric dipoles, magnetic dipoles don't feel a magnetic force in a uniform magnetic field. So there's a force, however, on a dipole in a non-uniform field. And you may have talked about this in Physics 118, but if we have a situation where, let's imagine I have a magnetic field that's varying in magnitude in the z direction. So let's assume positive z is up, and I'll label those magnetic field vectors and assume that this is uniform across the page, so that the field is only changing. So we have plus z here. It's only changing as we go up the board. If I have a magnetic dipole mu here, right, it turns out that this magnetic dipole will feel a force in the z direction. And that force goes like this, that the force, the z component of the force on the dipole goes like the z component of the magnetic dipole moment times the derivative of the z component of the field with respect to z. Okay. In advanced E&M, you'll sort of generalize this using vector calculus, but this will suffice for now. The key takeaway is that what is required for a non-zero force is to have a non-zero derivative, namely I need to have a spatial gradient of my magnetic field. And then the same thing applies in other directions. So, for instance, the x component of the magnetic force on a dipole would involve the x component of the magnetic dipole moment and partial b x partial z. Let me now remind you about what you read about regarding the Stern-Gerlach experiment. It's interesting that historically, Stern and Gerlach did not realize they were dealing with spin when they were first doing this. I'll post a link to a really fascinating historical article from Physics Today, which I had a lot of fun reading. Anyway, what Stern and Gerlach did was the following. They prepared atoms that were in an L equals 0 state. Okay. So one thing that Knight kind of brushed under the rug was that they weren't actually doing this with hydrogen atoms. Rather, they did this with silver atoms. It turns out that silver, the physics ends up being dominated by sort of, there's an outer electron in silver. There are sort of, inner electrons that turn out not to matter. The details of that are a little bit beyond us. But suffice it to say that silver, for the purposes of their experiment, behaved in a hydrogen-like way. Okay, so they prepared these atoms in an L equals 0 state. Right? So according to Schrödinger, right, such an atom should have, so if L equals 0, that means the eigenvalue of orbital angular momentum squared is 0. And then this means that the magnetic dipole moment of such an atom should be 0. What they then did was to send these atoms through a gradient of magnetic field. Right. And for purposes of this argument now, let's assume that their field gradient was in the z direction. So, namely, we can talk about a dBz dz. Right. So here's the case, right? If mu equals 0, right, then there should be no force on my atoms. And, right, the atomic beam that they're shooting through this magnetic field gradient should not be affected by the magnetic field at all. So, beam should not by that magnetic field. However, that is not what actually happened. So, in a second, let me erase the board and then tell you what actually did happen and what that tells us about the electron. What actually happened was the following. Namely, their atomic beam turned out to be split by their magnetic field gradient. What this implies then was that something must have been exerting a force on the atoms in their beam. And the only way to get a magnetic force is to have a z component of your magnetic moment with a z component. So atoms did have a mu z. And because of the nature of that split, right, that magnetic dipole moment could either point in the plus z direction or in the minus z direction. So pointing points in plus or minus z, or has positive or minus z components, it would be better to say. So, then the question becomes, where is this magnetic dipole moment coming from, right? Where is since we know that they prepared their atoms with L equals 0, and hence no orbital angular momentum. It turns out you can explain this using the following idea. Electrons have an intrinsic angular momentum, namely their spin. Now, the spin of an electron, what I mean by it being intrinsic is that it's a fundamental property of the electron, like its mass or its electric charge. So if we have the spin angular momentum, right, so S, right, can have a z component, right? So we can talk about the z component of the electron spin. Just like we had argued before that orbital angular momentum could give rise to a magnetic dipole moment, Stern-Gerlach are arguing that this spin angular momentum can give rise to a magnetic dipole moment in the z direction, and that's why, and that would explain the splitting that you observe. We can then ask the question of how to mathematically describe the spin of the electron. So remember how I talked about last time how you can write down an operator, so Lx or Ly or Lz. So like we have operators Lx, Ly, and Lz that describe the orbital angular momentum, we can write down, it turns out, an operator that describes the electron spin. We can write down Sz, and I'll just focus on Z for now, since that's the one that matters for just talking about this Stern-Gerlach experiment. So there's some operator, and it turns out, right, there are exactly two eigenvalues. Right, that a measurement of the z component of spin turns out to give you either plus h bar over 2 or minus h bar over 2. We can say that this is like what we did before if we say that Sz equals some other quantum number m sub s. Right. This is now analogous to the eigenvalues of Lz with m sub s equaling plus or minus 1/2. Okay, so that's sort of worth knowing about. This was in the reading. What I'm going to describe now goes a little bit beyond the reading. It's sort of for your edification, and again, will be discussed in considerably more detail in Physics 421. So what is this? What are these spin operators? Well, it turns out, right, if I have, right, something that can be has only two states, like down, up or down, right? So there's only two possibilities, sort of suggests sort of that the space of possible spin states is two-dimensional in a way that's radically different from how, like, 1D quantum mechanics that we talked about, that was infinite dimensional. So I'm not going to try to go into complete detail, but it turns out that you can describe the operator associated with one of the components of spin as a 2x2 matrix. So it turns out, and Physics 421 will work this out, that the spin operator can be written as a 2x2 matrix 1, 0, 0, minus 1, acting on things that we call spinors. So the spinor is what describes the spin state. It turns out that we can write the spinor, and I'll sort of corresponding to the eigenvalue h bar over 2. I'll write this as chi plus Turns out we can write this as a column vector, 1, 0, and the eigenvector corresponding to the eigenvalue minus h bar over 2, I'll call that chi minus, and that turns out to be 0, 1. So sort of colloquially, we call this spin up, and we call this one spin down. And this is again the eigen vector with eigenvalue h bar over 2. Just to convince yourself that this formalism kind of makes sense, I can go and apply this operator to this vector here. So if I apply sz to my spinner chi plus, I have h bar over 2, 1, 0, 0, minus 1, multiplying 1, 0. So if you remember how matrix multiplication works, I'll pull the prefactor down in front. So I've got 1 times 1 plus 0 times 0, which gives me a 1. And then I have 0 times 1 plus minus 1 times 0 equals 0. So look, this is what we mean by an eigenvector, right? Notice that this, right, applying this operator to this vector gave us the same vector back multiplied by a constant. This is what it means for something to be an eigenvector. So hopefully I've convinced you that this is in fact an eigenvector of this spin operator. And you can go and check that this chi minus is also an eigenvector with eigenvalue minus h bar over 2. So let me erase the board, and then I'll just sort of summarize what we can say about describing the full quantum state of an electron in hydrogen. So to completely describe an electron in hydrogen, let's assume that it's an energy eigenstate. It turns out what we need to do is we sort of have to take its spatial wave function. So if we assume an energy eigenfunction, I'll write that as psi nlm r theta phi. Whoops. And then it turns out we have to multiply the spatial wave function with a spinor. And so I'll just write that as chi. It could be a spin up or a spin down eigenstate or like a superposition, but also I'll just leave that there. So multiply by a spinor here. There's no spatial dependence whatsoever in this, so like we can totally get away with sort of ignoring the spinor when we're thinking about the spatial part of the wave function, and then just as well we can, if we are only interested in spin, we can think about only that piece and ignore all the spatial dependence. Okay. So a couple of remarks. In a second I'm going to go and cut away to my computer because there's a really cool historical postcard I want to show you that was sent by Walter Gerlach to Niels Bohr. So literally the raw data from the Stern-Gerlach experiment. But a couple of points. So it turns out that I can do this sort of thing. I can measure other components of spin. So instead of having a magnetic field gradient in the z direction, I can set up a magnetic field gradient in like the x direction, and I'll actually show you that in a simulation later on in the class. So we can measure that. Other point is sort of what is spin. As I mentioned, spin is an intrinsic property of the electron. It may be tempting to think of an electron as like a spinning ball of charge, like sort of like how that's sort of orbiting, kind of like how the Earth is orbiting the sun, yet the Earth is also rotating on its own axis. This is really tempting, but it's also wrong in the sense that if you try to think about sort of turns out if you work out order of magnitude, how fast would an electron actually have to be spinning, you start to get nonsense very quickly. You shouldn't think about the electron as a spinning ball, because it's not that. The electron is, as far as we know, a point particle that has no internal structure whatsoever. So you should just think of the electron spin as just something that it has, kind of like, it's like asking sort of where does the charge of an electron come from, and there's not really a completely satisfying answer to that question, I think. In the same way, it's hard to completely answer what is the spin coming from. It's just something we sort of have to accept as sort of part and parcel of how nature works. The last point I want to make before I go to my computer is sort of, I've introduced you to a little bit of formalism, like the spinner thing. Don't worry, I'm not going to ask you about spinners on the final. But this is a plug for 421. Namely, that 421 starts with analyzing spin in detail. As you've kind of already seen, analyzing spin and operators associated with spin involves like small matrices and column vectors. In some sense, that's mathematically a lot easier than the 1D quantum mechanics we did. There are no integrals when you're dealing with spin. And so 421 is a really fun way to begin sort of a more advanced study of quantum mechanics that in some ways brings in like more sophisticated conceptual ideas and math ideas from linear algebra. So go and take 421 the next time it's offered. And so now I'll cut to my computer, and then in the next segment we'll talk a little bit about some wacky quantum stuff with multiple Stern-Gerlach devices. So this just shows a postcard that Walter Gerlach sent to Niels Bohr showing initial results from the Stern-Gerlach experiment. Now, in this postcard, right, the way they've oriented the picture, the magnetic field gradient is horizontal, which is different from the picture that was in your reading, but the same thing holds. So the picture on the left here, right, so this is this streak is their beam of silver atoms. So it's silver with no magnetic field. So no magnetic field, no field gradient, and therefore there should be no splitting whatsoever. Here with the magnetic field, right, you can see how that pattern got split into two, and they only really had the maximum field inhomogeneity here in the middle, which is why you sort of see this like lip-shaped pattern over here. So I thought this was a really cool picture for you all to see. So his handwriting is really hard to read. So I think this, if I looked up what the German is, it's something along the lines of, here is the experimental confirmation of space quantization, which is sort of archaic language for all of this, and then something like, congratulations on the success of your theory. You can probably read Theorie here, and then you can maybe see that that's the signature Walter Gerlach at the bottom there. One final side note. If you go and read the Physics Today article that I'm going to link to, it turns out that a key technical part of the Stern-Gerlach experiment turned out to be the fact that they actually smoked bad cigars in the lab. I don't suggest that you do not go and smoke in lab, but it's actually kind of wild that turned out to be something that mattered in their